The winner. Okay. Oh, wow. Okay, that was like a photo finish. Okay. Well, hello to all y'all. Hello. Hi, and she comes. What? Oh, wow. Okay. Hi, everybody. Oh, wow. You guys are fast. I'm going to start with hello, Eric. Good to see you. And you are very fast in your own very, very um like subtle way. I'm gonna do this backwards just to, yeah. So well, now I'm getting confused. Okay, hello, Elizabeth with an S. Hi, Newell with an N. Hi, now this is getting confusing. Wait. Hi, oh, this is harder to do than I thought. I'm trying to do it backwards, but hi, JLo, whose name I'm totally pronouncing correctly, and I don't even know why there would ever be any confusion about that. Did I say, no, I can't do it backwards. It's too confusing. Okay. Hi, John. Hi, Maisha. Hi, May. Hi, Maisha. Second time. Hello, Newell. Hello, Jayla. Hello, Eric. Hi. Okay, now it gets crazy. And then hi, Lizzie, who's always just like subtly just like waiting for a proper moment, like not fighting with people, just being at peace, being a Jedi sort of warrior of physics. Okay. And hi, May, who, not Jaime, but Jaime. Okay, I'm going to stop this nonsense. Oh, group mates, interesting. Okay. Oh, new lab mates, I guess. Okay. And the, oh, three. Okay. I don't totally get I sort of get, I guess it's like a smiley. Okay. Whatever. All right. So hello. I owe you things as always. I'm going to say, okay, so what's going to happen today before I get all bogged down, which I always do. Yeah, no, we are going to go over the practice exam. I mean, good question, but I want to keep going over the practice stuck part 3. Wait, yeah, okay, no, good to know. And I do want to answer questions about the practice exam. Wait, but wait. Oh, wait a minute. Okay. Oh, hang on. I think if John Ford, if you're, this raises a good question. Are you asking about, okay, let me say to everybody, in a minute, what we're going to do, the main plan for right now is to go over another piece of the practice exam to help you practice for the exam. I mean, I think that would be the thing that would directly put the most minds at ease and be the most directly helpful, like to your grades and stuff. But John Ford, when you say you're stuck on part 3 of the homework, do you mean part 3 of homework 2? Do you mean part 3 of homework 2, part 3 of the math methods thing? Do you mean the vector stuff? Is that okay? So totally fair question, and I'm glad John's raising it. Let me make clear to everybody that I signed it because in principle we need it. Well, we need it for life and we need it later and all this, but let me make totally clear. The vector part of homework 2 math methods, the vector part, and I guess it is part 3 or part 4, the vector part is not on this exam. Let me just say that clearly. I mean, it's still a legitimate question on John's part. It's still a legitimate concern, all of that. But you do those vector things like the dot products and the cross products, you do not have to worry about for this exam. And therefore, to be more clear, I'm saying, like, don't even worry about them this week, like, period. What I would love people to be working on physics this week as we approach the exam, but you would not be serving your own time well if you got distracted with that this week. So I don't want to keep, so I don't want to like, fair question. Ultimately, it would be great to finish that for points. It would, but it's definitely your last. I would do those vector things on that homework if and when you've done everything else, and when we're past this exam. Like, don't let it distract you before this exam. But sure, afterwards, certainly you'll get points for doing them. And I will talk about them in class, but yeah, let's put those to the side for now. I mean, again, it's a totally fair question. It's more than fair. I mean, it's like an important question, but the answer is like no, or the answer is yeah, okay, fair enough. And don't worry about it. I would imagine that you wouldn't be sure how to do the last part. Totally, I've never said anything about them yet. I mean, in theory. Okay, so I'll say one quick thing about it. I mean, these are good questions, but then I don't want to stay on that because I don't want to confuse everybody. But yeah, that roof symbol, okay, just to say that roof symbol that appears on vector letters, the caret thing, whenever that, when an arrow is shown above a letter, that means that the letter stands for a vector. When that caret roof symbol thing appears over letter, it means that the letter stands for a vector, but specifically a unit vector. It means that that quantity has direction, just like any normal vector, but by definition, deliberately has a magnitude of 1. It means it's a vector pointing in a certain direction, but only has a size of 1, like on purpose. So it's called a unit vector. That's what that means. Again, a very legitimate question, but I don't want to say too much more about it right now because it's not on this exam. It will throw people off. Totally fair. I will get back to it. And I know I signed it before, so I totally appreciate that you care about it, but you don't have to care about it right now. But yes, good. So, but it means unit vector. That's what that means. It means unit vector. Yeah, so it's okay. Totally. So it's totally okay if you hand it in after I go over it. Yes. And if I don't ever go over it, then I will not even, then you don't have to at all. Right. Okay. So let me go. So okay. I'd like to, all right, hold on. Oh, well, there is actually homework 3. Yes. And that's good practice. There is a homework 3 and it is good practice for this exam. And it's very much like the first problem of the first part of this exam, this practice exam. Well, this real exam. The homework 3 was called like a heat harmonic hypothesized or something like that. It was called a heat harmonic. I'll check. Okay, I'm going to check really quickly unless I messed up. But I think that's in your classroom, and that would be good. To everybody, and I'd like to get on track here, but to everybody, what I would be spending my time on this week, first and foremost priority, would be the practice exam. And that's what I wanted. The exam, the midterm exam, will be posted this Thursday evening. You'll have until Monday to turn it in. In fact, I'm going to remind myself. So for today and Wednesday, I'd like to spend some time like trying to go over aspects of the practice exam and possibly answer questions about it. Although today, I've gotten enough questions about something that I want to just do it right away, whether you specifically ask or not. I've lost my train of thought. And I will try to post solutions to whatever I don't go over in class. If I go over something in class, like I'm about to right now, I'm going to give you the solutions right now. So I'm not going to separately also post them like you want to take notes on what I'm about to say and get the PDF that I'll publish. But I've lost my train of thought. But so what I would be doing if I were any of you, this week I would primarily focus on going over the practice exam, and particularly this coming Wednesday when we have our last class. Okay, but okay, wait, okay. Hang on one second, folks. Okay, hold on one second. Just trying to, okay, I'm getting a lot of questions in the, okay, I'm going to try, okay, to answer the questions in the chat. Well, the most important thing is what Stephanie's asked in the chat. Like, yes, and this, it was made clear in Google Classroom, and hopefully, and I think you guys even got points for responding and confirming your understanding of this. Like, the exam will be posted this Thursday, like in 3 days, which means we have today to talk about it, to talk about the practice exam, and we have Wednesday to talk about it. So I really do think we want to be focused on it for the next 2 days. It'll be posted Thursday evening. It's due back 12:15 p.m. Monday, like this coming Monday. And yeah, I think that, I mean, if there's any lack of clarity about that or any questions, you definitely should, I mean, either put them in the chat or from here on in, you should text them to me if there's any, but it is, I think, clear in Google Classroom that the exam will be posted this Thursday, due back on Monday. Like it's totally take home, open universe, all of that. And as far as, so that's Stephanie's question. And you might even want to make it, this is important enough that if there's any confusion, like whether you Stephanie or anybody else, like please put in the chat if I'm still not being clear, or if it's not clear, or if there's some or if somehow I'm contradicting myself somewhere or something. I would like to know. Okay, cool. Thank you, Jim. Awesome. Thank you. Now, as far as John's questions about solutions, what I'm trying to say is I'm going to solve some of these right here in class right now and Wednesday. Ones that I don't solve in class, I will try to post on Google Classroom. Yes, like whatever I don't literally solve in class, I will try to have up for you in Google Classroom. If anything that is, when I give you a solution, like I'm about to right now, what it means is that on the actual exam itself, I will vary the practice problem slightly. Like you're getting a practice problem now, I'll solve it for you. And then I'm going to make it slightly different for the actual exam. So you actually have to think about something. So you don't just like copy your practice exam there, but it'll still be very similar, but I'll tweak it just enough that you have to think or do something original. Anything that I don't post, if there's something where I don't post the solution at all, if I don't give you a solution at all by Wednesday night or by Thursday, that probably means that problem will exactly appear as is. On the practice. So I'm not even giving you a solution in advance because like I'm giving you just the advanced problem itself and plenty of time, advanced warning to work on it. So more solutions will be coming, but the faster I can actually get to the solution today, that will be one more solution that you'll have. And yes, anything left, certain things left over, I'll try to post on Google Classroom. But if so in other words, I'm not promising to give you 100% of the solutions to the practice exam. I'm promising to give you a lot. And I'm promising you that whatever I don't solve in advance, then you can rest assured that's going to appear like verbatim on the real thing. And anything I do solve in advance will be slightly tweaked for the real thing. So sort of there's advantages and disadvantages of both. But I would definitely, okay, cool. Oh, thank you. Okay. Whew, okay. But thank you guys. These are good questions. If I sound frenetic, no, thank you. No, now see, now we're talking. Okay. No, thank you guys. And again, all of you, I mean, okay, cool. So, and if you've participated at all today in class, like with these questions, like, and especially if you then like said, okay, now I get it, like totally submit those for points, please, in like the closing a conversational loop portal or whatever. But yes, cool. I'm glad you think it's fair. I'm glad it's clear. And, even more, I mean, no, I'm glad if you think it's fair or whatever. The most important thing is, first of all, do you think it's clear? Like, do we all understand what we're talking about here? It sounds like maybe we do. So good. So thank you. Okay. So I'm a little bit frenetic now because I'd like to solve another one of the problems in the practice. I have one in mind to do. Frankly, I think it went pretty well in the other class. Okay. Sorry. Well enough that I think it's worth doing with you guys now. But again, the more you can try the practice exam on your own, that's the best thing you could be doing with your time over the next 3 days. And the more specific questions you come to while you're doing the practice exam on your own, the more specific questions you come to, like in problem 2, part 3, I got a minus sign for step, is that right? Or should I use sine or should I use cosine or something? If you have specific questions like that show that you've actually tried the thing and then you're hitting a specific bump, definitely text me those questions. Remember, I would much more happily and more successfully respond to a great number of short, sweet texts than a small number of really long, vague texts. If you can write texts where it takes you longer to write the question, then it'll take me to answer it. That's a very good sign that you can write me a lot of them. Like literally, if you can write me yes or no or multiple choice questions, like, yeah, should I do this or should I do this? Or I will answer pretty quickly, hopefully, especially if it's about the practice exam. Don't text me when our solution or can you solve problem 2? Like I'm telling you, I'll do the best I can, but that's too open-ended and it'll take me you get my point. The more concise and certainly don't text me, can you teach me waves? Like, what am I supposed to do with that, right? especially in the text. Like maybe there's a Bitmoji that can take care of that question. But but do feel free. The more you actually are studying the practice exam and hit specific bumps in the road, text me those or email those kind of specific questions. That's funny. That's funny. Okay. All right. So now what I'm going to do is I'm going to turn. I think we solved a little bit of one of the practice problems last Wednesday. We went over like part B and A of problem 1. I'm going to deliberately now, follow me, don't lose me here. I'm going to deliberately turn our attention to problem 5, which is the very last problem of the practice exam. I'm on purpose going out of order, like, because I think this is the most useful thing to do. I'm turning to, well, I'm going to show you, I'm going to change the screens for a second. It says here, but I'm going to go to page 5 of the practice exam. And it is, excuse me, page 8, problem 5. This is in an update to the practice exam that, remember I said that could happen. Like I published the practice exam, then a couple hours later, I published an updated version. It had this page in it. If you only just downloaded the practice exam once or only printed it once, you might not have seen this page. So this is part of the reason I want to go over this one now to make sure everybody has it. I'm going to switch screens for a second so you can see what I'm talking about. Look in the chat first. Oh, that's funny. That's funny. All right, I'm switching pages for a second. Bear with me. Great. I'm switching screens for a second. Bear with me. Great. Right. Okay. Right. So I'm talking about this page of the practice exam. Again, if you only just downloaded the practice exam the first minute it got posted, you might not have seen this. It's an updated version. This page is what I want to go over like now, this problem. If I get going, I should be able to do this all within this period. Again, if it raises questions in your mind about other things, just make a note of them and text them to me or whatever. But this question is about the most recent material we did. Like first on Wednesday last class, we did an early problem in the exam to review the fundamentals, the earliest material. All the material only makes sense if you really know the fundamentals and the early material. But now I want to make sure that you still are getting the material we were most recently doing right before I announced the exam. So here's the problem. It's on the screen now. Please have it out in front of you, like in your own screen or whatever, because of course I'm going to switch back and start showing you a solution to it. Okay, so this is the problem. It's about the wave equation and all that. Okay, I'm switching back. Warning, warning, I'm switching back screens if I remember how. Okay. Maintaining the view. Okay. So, all right. So we're on the practice exam, page 8, problem 5. Now, I'm just right here. I haven't started solving it. I'm just like giving you some notes, some teacher notes to remind you of like the kinds of things that are going to be dealt with in this problem. This problem is all about the wave equation. I wrote the wave equation, the one-dimensional wave equation. I wrote it. That's the first line that I've written right here is the wave equation. Now, it's written one way. Part of this, we're learning concepts here and they're expressed as equations, but there's often more than one way to write an equation, more than one way to express a concept. And we want to be flexible and non-rigid about that. So that's the wave equation right there. And obviously it's your job ultimately to know what each symbol means and how they're all fitting together. But just note, even just that wave equation, like partial y, partial t equals v squared, partial y, partial x. Notice a lot of times in books, or maybe even on the exam, it could be written, here's another way it could be written. It could be written with the v squared in the denominator. And if you see that initially, you might be like, wait, what? Oh yeah, I thought I remembered it the other way. Like what? Why is the v squared in the denominator? But that's because I divided both sides by v squared. If I had wanted to isolate the space derivative on the left-hand side rather than the time derivative. Like notice those are equivalent and don't be thrown by that. I tend to write it the first way, but you shouldn't get confused or upset if you happen to see it written the second way. Often it will be written the second way in books. Okay, that's just. Now, what's that V? Quick reminder, that V in the wave equation means what I call the propagation speed of the wave, the speed at which the wave is propagating along the x-axis. Often in textbooks or with tutors and stuff like that, it's called the phase velocity, and in your lab, depending on who your lab instructor is, some people will call that V the phase velocity. Same thing. It means the rate at which phases of the wave, the rate at which like wave fronts are flowing along the one-dimensional medium, flowing along. So that's a horizontal concept. That V is how fast this wave is moving along the x-axis, assuming the way we've written it, okay? Now, where did it come from? Why, like, how is it in the wave equation in the first place? Well, look down for a second. I mean, I don't mean to jump around, but notice in the blue, all the way at the bottom of the page, in the blue version of the equation that's sort of circled, it says partial y partial t squared equals omega over k squared times partial y partial x squared. That's the way we originally, that's the first time we ever saw the wave equation, at least in lecture. It looked like that, okay? It was a partial derivative on the left side, it was a partial derivative on the right side, but the constant of proportionality was omega over k. Where did we get that from in the first place? So again, this is me teaching right now. I'm just trying to remind you and refresh sort of the background behind this problem that's being asked on page 8. I'm reminding you that where that came from, where that differential equation for waves came from is we had this cosine expression, y equals a cosine omega t plus kx. That cosine expression came from two places. One, it came from lab 3. Really, that is the result of finding out that when you send a wave pulse down a long slinky, the height of the slinky is a cosine function of time, as long as you look at any one horizontal position. And it's a cosine function of horizontal position, as long as you look at any one given snapshot of time, right? We found in lab 3 that the height of the slinky, when you send pulses along a slinky, the height of the slinky is a superposition of cosine functions. It's simultaneously a cosine function of time and of horizontal space. So in lab 3, we found that y equals a cosine omega t plus kx. But also in lecture, we set up this whole idea of a collection, a horizontal collection of vertical oscillators, all staggered in phase by a constant amount. Like that was an independent thing we did in lecture. We considered, what if we have an oscillator here, an oscillator here, an oscillator here, an oscillator here, and what if they're all identical in all ways, and what if they're equally spaced along the x-axis, and what if they're all free to oscillate along y-axes? But what if we stagger their phases so that when the first one starts, the next one is like pi over something already ahead in the cycle. And when that one starts, the next one is pi over something ahead in the cycle, and that blah, 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 blah. What if they're staggered in phase by a constant step? We realized that the one equation that could be used to describe that entire horizontal collection of vertical oscillators would be this statement, y equals a cosine omega t plus kx. In other words, from lecture, we found that statement, and in lab, thinking about a collection of phase staggered oscillators, and in lab, we found that statement looking at taking data from a pulse traveling horizontally along a slinky. So we decided, oh, a vertical pulse propagating horizontally along a slinky is equivalent to a horizontal collection of phase staggered vertical oscillators. Like, that's where lab 3 and the lecture are supposed to be converging, is that we're ultimately saying, oh, a wave pulse is a collection of staggered oscillators. So a wave pulse can be described by that cosine equation at the bottom of the page. That cosine equation, again, please remember, is very similar to, and in fact built from, our old cosine expression. Like in some ways, the evolution of this course so far, I mean, the evolution of this material, in some ways, is just us discovering a cosine function and making it more and more complex, more and more complicated as we progress. First, we just had y equals a cosine omega t. That was an oscillator. Then we had y equals a cosine omega t plus phi, plus a numerical constant. That was a oscillator starting at some other place in it, starting with a phase head start or phase delay. Now we have y equals a cosine omega t plus kx. That's a bunch of oscillators spread out along an x-axis. Oh, so okay, I'm looking. Looks like a good question. Hold on one second. What was the question? One spring wave pulse is essentially the same as a group of spin, but it just so happens to be. I think I definitely like John Ford's question. I think I want to say the answer is yes. I'm not 100% sure I'm interpreting the question correctly, but one spring wave pulse. But the only problem I have with the question, I think I want to say yes. I definitely like the attitude of the question. Like it's the right way of thinking. My only sort of problem with the question is, strictly speaking, if you're hearing what I'm saying and you're hearing what John's saying, I definitely am saying that a wave pulse is built from a bunch of oscillators. Each oscillator is like an omega t thing, and the whole collection of them together making a pulse is omega t plus kx. And I think that's partly what John is making sure of or saying, and I think I agree. The only thing I want to add to that, though, that might not be what John's saying. Oh, wait. Oh, okay, that's really interesting. Okay, and then I may have to go back to what I was saying, but so, all right, I like the follow-up that John's saying, but let me finish one thought is, I just want to make clear to everybody, wave pulses are definitely built from oscillators. You can't have a wave pulse without an oscillator, so that's true, but it doesn't go, like all squares are rectangles, but not all rectangles are squares. All wave pulses are built from oscillators, but one oscillator by itself is definitely not a wave pulse. Like you can't have a wave pulse with just one oscillator. Now I'm just saying that. I don't think John is saying anything in contradiction to that, but I just want to say that. Now then John's second, it's not that the medium is. Yeah, right. Like, right, a continuous medium. Strictly speaking, when we ultimately send a pulse across a medium like you did in lab 3, we're ultimately picturing that the medium is continuous, which means we're really taking, it's true, we're taking the concept of what I'm saying about a collection of staggered oscillators and we're really taking that to the limit. I mean, I think this is what John's saying, and this is right, that I'm asking you all to you can build the concept of a wave pulse in your mind from building in your mind a big arrangement of oscillators. The more oscillators you have and the closer they are together and the smaller each one is, the closer you're getting to a true model of a true realistic continuous wave pulse. So indeed, right, a true wave pulse like you did in lab 3 would be a phenomenon created by, like, truly would be like an infinite sum of infinitely close phase staggered oscillators. I mean, in that sense, John's absolutely right. Like for the wave pulse to really be real, like you saw in lab 3, this collection of oscillators that I'm asking you to picture has to actually be a super big collection, so big that there's actually an infinite number of them that are uncountable, that are all infinitely close to each other. That is true, and that's a really good point, what John is saying. Right, it's actually technically an integral. That's really good. Yes, yeah, that's cool. So somebody understands something. That's awesome. Yes. Okay, so cool point. So I'm going to go back to this now. So back to the page for a second. What I'm saying is that very last line on the page, The very last line on the page, the cosine function, we got from lab 3. We got from considering a collection of phase staggered, we got it from considering a collection of phase staggered oscillators and then saying, take that concept to the limit, like John was saying. Take it to the limit. Imagine the phase staggered oscillators are infinitely close to each other. And what you then have is what you saw in lab 3. So you get this expression, y equals a cosine omega t plus kx. Then what we did, which if I do have time today, I'll do for you again, I'll show you again, but I don't think I'm going to have time. What we did was we differentiated that equation twice. Well, really 4 times. We partial differentiated it twice with respect to time. And then we independently partial differentiated it twice with respect to space, to x. We took those 2 results and put them together algebraically. And we got this second order partial differential equation, the second to last line on the page here, the blue thing in a circle. We got d2y, well, partial 2y, partial t squared equals omega over k squared, partial 2y, partial x squared. That's what we got, you know, by the end of lab 3 analysis and by the end of whatever lecture a couple of weeks ago. That was our first glimpse at the one-dimensional wave equation. That is the one-dimensional wave equation. The way it was written the first time we ever saw it, the first time you see it in your notes, has us seeing that some kind of time derivative is equal to a constant times some kind of space derivative. A second time derivative is directly proportional to a second space derivative. That's what we're saying is the wave equation. So then what we did was we looked at that constant of proportionality. That constant of proportionality is omega over k squared. We unpacked that. We asked ourselves, what is omega? What is k? Like, what is omega over k? And now, so I'm kind of saying, I'm guiding your attention toward this board sort of upside down, like go to the middle of the board now. What we realized was, oh, omega over k. Now, again, this is in your notes. I'm not trying to reteach this. I'm just trying to review it. Omega over k. Here, the quick way we said this. Omega over k is omega is 2 pi over t. K is 2 pi over lambda. Like omega is angular frequency, cycles per second, but measured in radians. Omega is radians per second. K is radians per meter. So omega is like how many sixths of a cycle do we complete every unit of time? And K is how many sixths of a cycle do we complete every unit of space? They're like counterparts to each other. But if you put one over the other, omega over k, if you put, and you can work, we've worked out the units before, you could try it yourself right now if you want. I'm just running out of space here. If you put 2 pi over t over 2 pi over lambda, if you put radians per second over radians per meter, what do you get? You get meters per second. You get wavelength over period. Another way to put that is wavelength times frequency. What am I trying to say in this middle? What am I trying to say right here? I'm trying to say that omega over k is is the distance for a cycle divided by the time of a cycle. Omega over k is how far it is from one crest to the next divided by how much time you have to wait from one crest to the next. That is how fast the crests are moving through space. Omega over k is v. And then I'm also saying in this line, there's other ways you could think about it. You could think about it as omega over k. You could think about it as lambda over t. You could think about it as lambda times f. Why am I giving you 3 different ways to think about the same thing? Am I just trying to confuse you? Well, it's more that I'm pointing out to you that there are 3 different ways to think about the same thing. So so the capital T in this context is period of time. It's the reciprocal capital. I'm just answering a question in the direct chat. Like frequency is F. Capital T is, sorry, frequency is F, period is capital T. They are the reciprocals of each other. Like that is not clear. I want to write this in. Like period, capital T is seconds per cycle, how much time it takes to do a cycle. Frequency is cycles per second. They are literally the reciprocals of each other, the multiplicative inverses of each other. There's often in this course more than one, often in life, there's more than one way to say something. It's not that oh, cool. Okay, good. Okay, cool. I'm not trying to confuse you people by giving you more than one way to say something. I'm trying to alert your attention to the fact that there already exists more than one way to say something. What I'm really trying to say is omega over K is the most direct, is the direct mathematical way to capture the speed of the wave. Omega over K is what comes out of differentiating this cosine expression. It's what is explicitly contained in the math. But omega is kind of abstract and K is kind of abstract. They're kind of hard for us all to relate to. So another way to put them that I find easier to relate to is wavelength over period. Omega over K is the same thing as wavelength over period, which is to say distance per time of each cycle. So distance per time of the wave is the speed of the wave. I think lambda over T is the easiest way to picture or relate to speed. I think omega over K is the most mathematically explicit way to relate to speed. And I think lambda times F, the final way I'm writing it, lambda, like lambda divided by T is the same thing as lambda times F. Why am I writing it that way? Because almost all textbooks and almost all websites and in all your future science courses, it tends to be the case that when people talk about the speed of a wave, they say speed of a wave is wavelength times frequency. They do that because wavelength and frequency are like the two characteristic features or properties properties of a wave. So they put them together in that nice clean way. You've got the wavelength of a wave, like how far it is from crest to crest. You multiply it by the number of crests per second, and you have the speed of the wave. All those things are equivalent. They just are convenient for different contexts. Now, why am I spending all this time like reminding you of this? I haven't even done the problem yet. I know that. I'm just trying to remind you of the background going into this problem, that the point of this problem, problem 5 on page 8, is it's asking you to play around with a certain example of a certain wave as described by the wave equation. What I want you to know going in is, okay, know the wave equation, be flexible that there's different ways to write the wave equation, like this right here is, sorry, this is the wave equation. This is also the wave equation, just written a slightly different way. This is also the wave equation, written a slightly different way. I want you to be okay with that. Why am I saying they're all the same? Because I'm saying like V and omega over K are just two different ways of saying the same thing. But there's other ways of saying that too. Now, actually, we're going to play around with all these different ways in this problem. So that's why I'm just like putting them out there first, okay? And where did this wave equation come from? It came from differentiating this cosine solution twice. Last thing, I'm going to look in the chat again. I'm saying in the early material of this course, in the stuff that you practiced in problem 1 for the test, what you really, you're taking a differential equation, d2x dt squared equals negative omega squared x. You're saying that differential equation, that comparatively simple differential equation, applies to one oscillator or one oscillator, and then you're saying the solution to that differential equation is x equals a cosine omega t or something. Like in the beginning of the course, we have a differential equation that describes an oscillator. It has derivatives in it. Then we have a solution to that differential equation. It has a cosine in it. They both ultimately contain the same, they're both describing an oscillator. but one describes it holistically. It's basically saying the oscillator must obey Hooke's law. The other is the actual equation that you use to plug and chug, the actual equation that takes time as its input and gives you position as its output, a standard kind of physics function. So one is the differential equation, and the other is the solution and what becomes known as the equation of motion. That's earlier in the course, like problem 1, that's simple harmonic oscillation. Now I'm saying a blown up, more exotic, like slightly more hard version of that happens again with wave pulses. We have a differential equation that describes the nature of a wave pulse. And then we have a solution to it, which is this cosine thing. And the solution to it allows us to make predictions about exactly where things will be when. The differential equation describes the whole phenomenon. The solution gives us an equation of motion that we can use to make predictions, okay? The cosine is the solution to the differential equation. We want to have sort of both those at our fingertips as I now go into actually solving problem 5. That's exactly what I'm going to turn the page to problem 5. Let me just check there's something in the chat. Let me just make sure I'm okay with the chat. Oh, no, I answered it. Okay, cool. Oh, wait. Dude. Oh, okay. So I think, I did miss a couple questions in the chat. Sorry, hold on one second. Oh, okay. I think I've answered the questions in the chat. All right, so I'm going to turn the page now. So now we go. Okay, so now here is problem 5, right? As though I'm doing a solution to it, as though I'm the student or whatever, like there's a sample solution. Yours should contain all the elements of this, but of course it shouldn't be identical. So first I'm doing step 1, DFP, like the diagram and fact pattern. The facts that were given the problem is D2Y. Again, this is the thing that I just screenshotted a second ago or screen shared a second ago. D2Y dt squared equals 900 meters squared second squared times D2Y dx squared. That's a given. It's also a given that so say given some wave pulse described by that, given that the amplitude of the wave pulse is 5 meters, given that the angular wave number is 0.1 radians per meter. Those were all the givens, right? So this is diagram and fact pattern. Notice also, if I'm doing the solution, if I'm the student, if I'm taking this exam, notice also in the top right, I included a diagram. Notice the question didn't include a diagram. It's easy to forget. If we're answering, it might be easy or tempting to not give a diagram if you think, oh, well, the question didn't provide a diagram, so I don't have to. No, please. If the question, for whatever reason, neglected to provide a diagram, that's all the more reason that we need a diagram. So up in the top right, I've given a little diagram, and it's like 2 little graphs. I think it's the best, most concise way to capture the nature of a wave pulse. If I want to capture the nature of a wave pulse, one big lesson we're trying to get across in lab 3 is a wave pulse is really a function of 2 independent variables. There's horizontal position and time, both together, yet independently, driving vertical position. So to capture a wave pulse, it's not sufficient to just draw a wiggle, right? A oscillator is not a wave pulse, and a picture of a wiggle is not a wave pulse. An oscillating wiggle is a picture of a wave pulse, or a wiggling, or wait, what did I just say? An oscillating wiggle, like a cosine thing, a cosine shape in space, cosigning back and forth in time is what a wave is. Or put another way, a cosine in time, an oscillator, spread out cosinusoidally in space in a collection of many, many oscillators. You need both elements to make a wave pulse. You can't just have an oscillator, and you can't just have the shape of a wiggle. You got to have a bunch of oscillators in the shape of a wiggle, or a wiggle oscillating, right? That is, so my little 2 graphs up here, that's why in lab 3 you took a movie of a wave pulse and it turned into 2 graphs, not 1. Super important. Y is a superposition of a function of, Y is a function of X and a function of T superposed. That's what a wave pulse is. All right, anyway, so that's part of my givens. So I just did all my givens here, step 1 DFP. Again, you don't literally have to write out step 1 DFP, although you certainly could, and it wouldn't be a bad idea. But you do need to do a step one DFP. So there's my step one. So then step two, what is the question? The question is, it just says Q. That Q just means here's the question. So the question is compute lambda, the wavelength. That's what the question's asking for, the wavelength. All right, now, to get straight to the chase, the one equation I'm really going to need here to get lambda based on for this part A, given, oh, go ahead. Just looking at the chat. Yes, exactly. Good question, direct chat person. The answer is yes. I'm going to go on. Yes, good. Okay, now I'm going to say, you see this equation all the way to the, well, you see these equations. These two equations. In substance, yeah, those are like, oh, in fact, sorry, this should say. Yeah, those are definitions. Angular frequency is 2 pi per period. So it's radians per second. Angular wave number is radians per meter. They're like equivalent of each other. One is this angular wave number is the space counterpart to angular frequency, which is the time version. The truth is that this second equation is actually all I'm going to actually need and use to solve this part A. I'm just reminding you where like it applies, like what we were given a wave equation. We were given a number 900, which if I'm understanding my wave equation correctly, that 900 is a speed, right? Or speed squared. The speed can be broken down into an omega and a K. K is this thing here. They gave us K, they want lambda. So I'm turning the bit. So all I'm going to really use, so step 3 for general definitions and principles, this is the general definition and principle that I'm really about to use here. K equals 2 pi over lambda. So I've turned the page, or I try to turn the page. Okay, so K equals 2 pi over lambda. Now I'm doing the work. Therefore, lambda equals 2 pi over K. Now I'm just plugging in, like lambda equals 2 pi radians per cycle over 0.1 radians per meter. So I just divide. So I'm saying 2 pi is approximately, 2 pi is approximately 6.28, right? So if I divide 6.28 by 0.1, I get approximately 62.8. So that means the number of meters in a given cycle is 62.8 approximately. So the wavelength of this wave is 62.8 meters. That's it. That's part A is, as long as you know what you're doing, part A is just kind of an exercise. Okay, so that's it. That's the wavelength answer for part A. Now we go, part B is a little bit more involved. And we're really going to use all these equations, part B. Okay, part B, I could say C above for most of the, oh, yes, absolutely. Fair enough. Yeah, sorry. Okay, tell me when. Yeah, sure. Okay, thank you. Yeah, no problem. Okay. All right. So we're going to here. All right. So part B. No problem. Thank you. Okay. Part B. Oh, yeah. Okay. So part B, first of all, I said C above for givens, just to be clear. Like someone asked me in the class, like I've already mapped out most of the givens in the big diagram at the beginning of this. So I don't have to keep doing that every time for every part. I mean, that's fine, but I'm just referencing them. But then there's a little bit more givens here in part B, like it says, given T equals 3, X equals 10. And what's Y? So what we're really asking now, we're really trying to now physically understand what's going on in a wave pulse. Like we've got this long, again, I think picturing lab 3 is the best thing to picture at all times or try to draw. Like we really are talking about lab 3 here. You got this long slinky and you're shaking it. So you're sending pulses going horizontally, propagating horizontally back and forth along the slinky. That means at any given snapshot that we take for any given moment, like for example, T equals 3, like a freeze frame will look like a cosine, right? Like it will be like Y will be a cosine function of X. It's also true that at any given horizontal position, Y as a function of T is a cosine function, but that's not visually really what we're seeing at any given moment. Visually, at a given moment, we're seeing like crests and troughs in this slinky. And what the problem's really saying is, okay, let's pick a moment in time, like t equals 3. Let's scan our eyes over to a certain horizontal position. Okay, let's look over there at position 4, x equals 10 meters, which is kind of like saying, let's look at if we imagine this whole thing as a bunch of little vertical oscillators all next to each other, it's like saying, let's look at the 10th oscillator. And what the question's asking is, okay, how high is the slinky at that place at this moment in time? That's what it's asking. So on this picture, it's asking, like, what's the y coordinate of that point on the slinky at that moment? Okay. So that's a question that's asking us to make a prediction about vertical output given time and horizontal input. It's asking ultimately what we need here. Like, the wave equation describes the whole phenomenon, but for this plug and chug type question, we need that cosine function. Like, I'm just going to look at it. So the wave equation is partial y partial. The wave equation is what's written down here at the bottom of the page. I'm going to get the chat in 1 second. Like, the wave equation is what's written at the bottom of the page. But what I'm saying is, whenever we have that differential equation, the solution is this. Like, this is a solution to the differential equation, and we need the solution to plug into if we're being asked a question of this nature. So we're going to use this cosine thing. Now, again, I'm going to look in the chat in 1 second. Let me say, if I do happen to have time, which would be nice, what I'd like to remind you and show you is, how did we ever show that this was a solution to that differential equation? Or put another way, how did we get from this solution to that differential equation? Like, it was from differentiating twice. Well, it was really from differentiating 2 pairs of 2 times each. Yeah. Which I have time, it'd be useful to show you, because that's something you might want to, like in your exam, if you say this is a solution to that, you would be very well advised to then show me why, or show me how you know that by showing the derivatives. That would be a very good idea. Therefore, it would be a good idea if I could show you now, and I will try in a couple of pages or a couple of minutes, but I want to finish the problem first. Also, if I don't, it's definitely in your notes from last week and from lab 3. Let me pause for a second and just see something's happening in the chat. Hold on, sorry. Oh no, okay. Nothing is happening in the chat. Okay. All right, but so that cosine, so I'm going to plug into that cosine expression. I'm looking for y. I was given x. I was given t. So I'm going to plug into the cosine expression. I was given a all at the beginning of the problem. So I'm plugging in, like, so yeah, like, I'm plugging in to this cosine thing. I'm putting in the numbers. And I'm about to be done, and I'm all happy, and I'm taking my exam, and I'm like, yay, I feel like I understand this problem. And then all of a sudden I realize, oh no, wait a sec, I don't have omega. Like, I have one equation, but I seem to have 2 unknowns. Oh, yikes. Like, this would be fine if I had omega, but Yaverbam never gave me omega, or there never was an omega. Good point. Now, without me getting too excited, let me first of all caution you and say, if I were taking, well, yes, actually, that's really great. And I'm glad he went public on that one. John is definitely right. Omega is 2 pi over t. That's a really good point. And also a really good, yes, that's really true. But let me, and maybe I'll even use that in a second. But one thing, do we know t? I mean, like, in other words, if what John is saying is, hold on, you might not literally know omega, but don't you have enough information to get it? Oh, yes, I agree with that. Yes, I'm going to get it. And I probably will use something like 2 pi over t. It's just, it's not going to be that like falling off a log, because I'm not sure that I know t off the top of my head. Like, I don't think that was given. But John's larger point is very well taken, because let me tell all of you, if I were taking this exam, and especially now this is a take-home exam and it's open universe and everything, so, and that's meant so that you hopefully do take your time and you don't get freaked out by time pressure, and you do learn something as you go, blah, blah, blah. But just to caution you, if you're anything like me, if there's any feeling of pressure about an exam and you're taking it and you get to this point, if you're like me, what might happen to you is you might go, oh, wait a minute, I thought I was doing the right thing, but I don't have omega. So apparently there's two unknowns. So, oh crap, I guess I'm doing the wrong thing. And if you're like me and you, or like I was or whatever, like you might then panic or stress out and be like, oh, and then you might like start erasing this work or starting all over again or something like that. And I just want to remind you, don't do that. Like the fact that we are not there at the answer yet does not mean we're on the wrong path. It just means we still have to go farther down that path. Okay, so, and in fact, this is essentially what John is saying, like, wait, isn't there a way to get omega? Yeah, there sure is. So I'm going to turn the page. I think I'm more or less going to do it like he's saying. So I'm going to solve, so it says subproblem or sidebar, whatever, solve for omega. Okay, I'm going to solve for omega. Well, V equals omega over K. So this is, again, it's similar to what John was saying a second ago. And I think he could get there his way. This is my way. V equals omega over K, okay? So therefore rearranging, omega equals V times K. And I think we do know V and K, that's the thing. We don't know omega off the top of our head. We also don't know T off the top of our head, but K was given. K was given at the beginning of the problem as 0.1 radians per meter. And as for V, well, this is where the wave equation comes in. The wave equation is delta is partial 2y partial t squared equals v squared partial 2y partial x squared. And what we were given in the problem is we were given a 900 right there in that parentheses. That 900 is v squared. Therefore, and I'll get the chat in 1 second, therefore, the square root of 900 is v. V is 30 meters per second, I might add. Well, so I'll just finish this and then look at the chat, right? So the key piece of information that the problem actually did give us was that V equals 30 meters per second. Therefore, omega equals 30 meters per second times 0.1 radian per meter. Now, I'm going to turn the page in a moment, of course, but that'll be omega. We're not done with the problem. The question of the question, if I did step 2 WIQ, the question was what's Y, but we realized we need omega to get Y. So now we have omega. So now I'm going to go back and continue, but let me just look at the chat. Oh, I keep doing that. Yeah. Why does it appear? Okay. So yeah, I did answer what's in the chat, I think. Okay. So now I'm going to turn the page. All right. Okay. So omega equals 30 meters per second times 0.1 radians per meter. So omega is 3 radians per second. Pause for a second. Notice this. Omega equals 3 radians per second, not 3 pi radians per second, not pi radians per second, just 3. Is that okay? Yes, that's totally okay. Let me make clear again, like radian is a section of a circle. It's approximately a sixth of a circle. 1 radian is like about 57 degrees, which is to say slightly less than a sixth of a circle. You can have 1 radian, you can have 2 radians, you can have a half a radian, you can have 3. It's just that if you have any integer number of radians, you're not perfectly filling up the circle. It takes 2 pi radians to go around a whole circle. So often our number of radians have pi's in them. Or like a half cycle would be pi radians. So, but there's no reason we have to have exact portions of circles. So just know, in other words, pi is just a number that's a little bit greater than 3. And 3 is just a number that's a little bit less than pi. The 3 radians per second is a perfectly legitimate angular frequency. And what it really means in English is a little bit less than a cycle and a half. Excuse me. No, it doesn't. It means a little bit less than a half cycle. That's all it means. So omega equals 3 radians per second. Now I've got everything I need to plug in to the cosine expression. I'm plugging into y equals a cosine omega t plus kx. So now I've got the 3 to plug in for omega, the 3 to plug in for seconds. Notice it's 3. I should really put the units in. It's 3 radians per second times 3 seconds. So those seconds cancel and you get radians time plus 0.1 radians per meter times 10 meters. So the meters cancel and I get radians, right? Radians plus radians is radians. So then I'm taking the cosine of something measured in radians. So I get y equals 5 cosine 9 plus 1, 5 cosine of 10. Can I take the cosine of 10? Sure. Just please, and you could do it on your calculator, of course. Just remember that your calculator your calculator must be in radian mode to spit out the right answer. If you do all of this correct, and then you get to the final step and your calculator is not in radian mode, your answer will be wrong. I will take off a couple of points because we really do need to understand and respect radians at this point. But on the other hand, I'll only take off a couple of, if you've done all this physics correctly and you've postponed the numbers to the last possible minute, as I tend to advise, then you're only going to lose a couple of points if your calculator just happens to be in radian mode. That's an advantage of doing all the physics and leaving the computation for last. But what you ultimately get is that y equals approximately negative 4.2 meters. So that means that if we were looking at this snapshot of your wave pulse, if you're looking at the snapshot of the medium at the 3rd second, and you let your eyes gaze over to the 4th horizontal meter, you would find that at that spot, you're finding a trough, not a crest. You're finding that the slinky is underneath the equilibrium axis, about 4.2 meters underneath. Is that all the way down? No, all the way down would be negative 10. How do I know? Because the all the way down would be negative 5. How do I know? Because the amplitude was given as 5 meters. So put another way, this is a reasonable answer. If we had gotten, let me say this, if I had gotten as my answer y equals negative 6.2, if I'm paying attention, that's a red flag. I would realize something's not right somewhere, because the thing could never be lower than negative 5 or higher than positive 5 if the amplitude is 5. So, but we got something reasonable. We got negative 4.2. So that's the answer to that question. Okay, we have 13 minutes left. We have one more part to the question, but hopefully that's involved. But this is all about picturing the wave equation and what it does for us. So in the last question again, it says in English, ultimately it says, all right, now let our eyes shift to another place in the wave pulse. Let's go to a place where the concavity, where we're looking at the curvature, the non-flatness, the disturbance, the deformation in the medium. We're looking to another place now where the deformation in the medium is half as much as where we were first looking. So what does that say about the acceleration downward toward the equilibrium axis? Well, the answer is it must be half as large. It's that simple. Because what I'm trying to get at in this question, so if I'm saying we look at a place where the concavity is half as large, what can we then say about the acceleration at that point? It must be half as large. And when I say acceleration, I mean the vertical acceleration toward the horizontal axis. Because what this wave equation means, I'm just asking you to understand that what this wave equation means is that acceleration acceleration along the y-axis, acceleration toward the x-axis is directly proportional to concavity. That's what the wave equation is saying. It's saying if you picked any spot, any point that you look at on the wave, the rate at which that point on the slinky, the point in the medium, the rate at which that point is accelerating back toward the flatness is directly proportional to how not flat things are at that point. That's the essence of a wave. The more deformed the medium is, the faster it undeforms itself. That's what all the rippling and the pulsing and the cresting and the troughing is all about. It's Hooke's law, restoration, just blown up into a higher dimension, right? Again, remember, go back to springs. What's the nature of a spring? F equals negative kx, or d2x dt squared equals negative k over mx. The nature of a spring is the farther away a mass is from where it wants to be, the faster it accelerates back to where it wants to be. That's what we're saying here. The more deformed the string is, the farther away it is from being flat, the faster it flattens itself. That's literally what a wave pulse is. It's restoration in time and in space. It's Hooke's law restoration in 2 dimensions of space rather than just one. It really is quite elegant, I think. But all right, so that's the end of that question. Like that would be the end of that question, except I want to, at the risk of, if that's clear, we have 10 minutes left. I want to now finish this. I want to do the page that, remember I said, I said, okay, with 8 minutes left, I'm very quickly going to do, for some of you, this might be old hat. For some of you, not. I'm going to take that cosine expression. I'm going to differentiate it twice with respect to time, and then twice with respect to space, and put the results together and show you that it gives us this second order partial differential equation. So I'm technically partial differentiating. Okay, so I'm going to turn the page again. We've got 7 minutes. I'm going to take, in effect, 4 derivatives and show you why. And that doesn't show where I ever thought of the cosine, like where I got the cosine again was from lab 3 and from considering a collection of phase staggered oscillators, but how I can show that it fits, that it solves this differential equation is by differentiating. So here we go. So here's the expression, right? And you might want to show a little bit more work than even I'm showing now. I'm trying to do this a little bit concisely because we have 6 minutes left, and also because we've done it before, but I just took one derivative with respect to time. How did I do it? I used the fact that I almost want, okay, no, actually, okay, wait, I'm going to take a risk here. Hold on, before I even write that, I'll just note. I'm just quickly reminding, okay, we have 5 minutes left. I'm going to do this fast. I'm just reminding you that, derivative of cosine is negative sine, derivative of sine is positive cosine. I'm also reminding you, and I could turn back the pages right at the end if you want. I'm also reminding you I'm reminding you chain rule. If right. Okay, so these are the two facts I'm not re-explaining this because I've explained it before. I'm running out of time, but I'm just reminding you that the two facts we're going to use to do these derivatives is trigonometric derivatives and chain rule. So here we go. So here's one derivative with respect to time. I've got 4 minutes here. So now I'm going to differentiate again. Here's the second derivative with respect to time. So I differentiate again. And I'm using chain rule. But remember, I'm taking partial derivatives with respect to time. So I'm treating x as though it's just a constant. So the chain rule, treats kx, the derivative thereof, as 0. Okay, so there's my second derivative with respect to time. Then I do first derivative with respect to space, and I get and then I take another derivative, right? Now the k comes out in that one. The omega does not, because now I'm treating x as a variable. I'm treating t as a constant. So like omega t, the derivative of that is 0. So I do that, right? So now I do this again, and I get negative a k squared cosine omega t plus kx. So now I have two different second derivatives, one with respect to time, the other with respect to space. I rearrange each one of them. I know I have 3 minutes left. I rearrange each one of them to solve just for the cosine piece. So I'm going fast here again. And of course, I'm going to post this PDF. So, and I'll hang out for a minute when I'm done if you want me to turn back to any pages, or just follow me for the 2 more minutes. I rearrange and say, fine, cosine of omega t plus kx equals or all divided by negative a omega squared. But also, that's from the time expressions, but also cosine omega t plus kx equals the space derivative all divided by that. So I set them equal to each other. So I set them equal to each other and say, okay, we're just about done. We have like 2 more lines. Right, and we're just about done. We have 1 minute. So I divide both sides by -1. I divide both sides by a, so they all cancel out. And so my final line of the whole thing, and this is the final line, multiplying both sides by multiplying both sides by omega squared, I get, and this is the last line, and then we are done. I get and that's it. That's what I did. We took two derivatives with respect to time, two derivatives with respect to space, put them together, and we got that. That shows that that cosine thing is the solution of that. That's it. I will hang out for 2 seconds. Well, I'll hang out for a couple minutes. If either A, you want me to turn back any pages, or you want to ask any questions or anything like that, but I'm done and you guys are great. And yes, bye. Okay, bye everyone. And I'll post the blah, 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 and blah, blah, blah. Okay, good job, everyone. Thank you for the question. Thank you. Thank you. Have a good, cool, awesome. I appreciate it. I do appreciate it. Oh, thank you. Oh, good. Oh, thank you. That's very nice. Thank you. And then bye. Yes, thank you for your kind comments. Okay, awesome. What are you guys still? Awesome. Yes, absolutely. I can.